We're starting section 6.2 on triple integrals over general solids. The goal of this section is to evaluate the triple integral of a function of three variables over a general solid instead of just a box like we did in the past couple of videos. As with regions in the plane, it's going to be useful to categorize solids into different types, and we're going to use three types. 6.2.1 triple integrals for three types of solids. Type 1. Type 1 is where the solid is going to be bounded top, bottom. So what does that look like? We're imagining that we've got a surface somewhere on top. We've got another surface on the bottom. Let's call these function names. u1 of xy will be on our bottom function. u2 of xy will be our top function, and that these are bounding a solid. And that solid, if we imagine projecting it down or a shadow of it down in the xy plane, will have some sort of shape here over which the solid floats in space. It might go through it, might be under, but it's the projection of that solid down into the xy plane. So that is the solid bounded top bottom. So what we're saying here is that solid S, right, this is our solid S, is the set of all points x, y, z in R3 such that, well, xy, the xy have to be in this shadow region D. So the xy are in a region D of the plane, and for every xy in there, the z is somewhere bounded between these two functions, so that u1 of xy is less than or equal to z is less than or equal to u2 of xy. So that describes the solid S. Now, if we want to take the triple integral over S out of this non-box-like solid, how do we do it? Well, it's defined here as the integral. I'm going to write an inner integral first. The integral from bounds, which are u1 of xy, to u2 of xy. So like when we were doing double integrals, we have variables in the bounds of our function f of x, y, and z. So that suits us very well from bottom to top. We feel very comfortable with that. Those are z bounds dz. So we write that as an inner integral. I'm going to write brackets around it. And then what's left is we're doing top minus bottom over this region D. So we make that a double integral over D, dA. And that double integral now, once we can evaluate that inner integral as an iterated integral, we'll do that one first. Then what we're left with is a double integral, which we know how to do. And just as a little remark, that double integral can be done two ways, right? D can be set up as a type 1 or a type 2 region. And if D can be a type 1 or type 2 region, then this integral, right, with a type 1 solid can be done two ways. So you can imagine that there's two more types. They can each be done two ways. There's going to be 6 total ways of setting up integrals potentially over solids. So what does a type 2 solid looks like? It will be, instead of bounded top bottom, it is going to be bounded front back. So that means that we're going to imagine that we have a solid or a surface here in front, another surface behind it, and that the solid is captured bounded between these. And this time we're going to imagine that this solid is projected back into the YZ plane. So that region D, I'll call it D again, is the shadow or the projection of that solid down into the YZ plane, which means that our bounds are going to be functions of YZ. So U2 of YZ will be our front bound, and U1 of yz will be our back bound. And so the solid S is going to be in a very similar way. All the x, y, and z in R3 such that now it's going to be all yz that are in this region D, and u1 of yz is less than or equal to x is less than or equal to u2 of yz. Similarly, to set up a triple integral, we'll have an inner integral, which will be in terms of these variable bounds, u1 of yz, it's almost exactly what we just did above, u2 of yz of f of x, y, z dx now for the inner integral. And that integral, once we've done the inner integral, will be set up as a double integral over the region D, which is the region in the xy plane, dA. And of course, that also can be done as a type 1 or a type 2. So two possibilities for the inner integral where the solid is bounded front-back. Type 3, well, what's left? We've got top-bottom, we've got front-back. What we are missing is left-right. So our type 3 solid will be a solid where we can describe the bounds as a left and a right bound. So our front bound will be, again in blue here, our back bound or our left bound will be in red. Again, we're imagining a solid bounded between them. So again, we're going to have a front function, we'll call it u2. Now the variables are xz variables. And the left bound is going to be u1 of xz, and in a completely analogous way, we imagine the projection of this. That looks a little too small. We're going to imagine the projection of this back now onto the xz plane. The solid, the shadow of that solid, or the projection of that solid back down onto xz. So our solid S is described completely analogously. So all points x, y, z in R3 such that now it is xz. X and z are in this region D, and u1 of xz is less than or equal to y now, is less than or equal to u2 of xz. And lastly, the last completely corresponding triple integral to set up a solid that's bounded left-right. The inner integral is going to have variable bounds, but now the integral will be in terms of y. So u1 of xz to u2 of xz of f xyz dy, and in the exact same way, that's going to be set up as a double integral over that projection region or that shadow region D now in the xz plane dA. And that, of course, can also be type 1 or type 2. So depending on how your solid is most easily described, some can be described all three ways, right? If your solid can be just easily described all three ways, and each shadow region D can be described in two ways, as type 1 or type 2, then potentially you've got six orders of integration for a function over a solid in exactly the same way, a general solid in exactly the same way that we did over a box. So in the next video, we are going to look at an example with actual functions and actual bounds and setting up these integrals in multiple different ways.